We live in a world that is dynamic and in color. But why is vision testing still in black and white and static? The current standard for vision testing was created by Dr. Hermann Snellen 160 years ago, using European-style letters for measuring acuity and refractions. The 1862 Snellen test was a major technical achievement for its time, but it requires literacy with European-style letters. It also measures vision only in black and white. It is difficult to use with children or infants. It is inherently inconsistent due to having an inconsistent stimulus gap. And it is inherently imprecise due to static letters depleting the photoreceptor response. Acuity is the measurement of visual clarity. Refraction is the process of using the measurement of cylinder, axis, and spherical lenses to compensate for optical errors in the patient's eyes. As for why most people need vision testing, myopia is the difficulty in clearly seeing distant objects. Myopia is the most frequent reason for vision correction and affects 22% of the world's population. Snellen methodology requires patients to correctly guess 4 out of 5 non-identical letters on a line to correctly determine their acuity. As a result, it often results in prescription errors. Static vision testing also consistently adds excess minus power to acuity and refractions and may be increasing the global problem of myopia. The solution? Introducing the diop, the 21st century method of dynamically measuring vision and in color. A diop is a spinning segmented ring used as a visual target. A diop uses the physiology of vision rather than culturally dependent letters to measure acuity. As the diop gets smaller, the acuity endpoint is the smallest diop ring where the direction of spinning is detected. When using a diop for vision testing, 2 diop rings are displayed, but only one of the diop rings is spinning. The patient is asked which ring is spinning, the left ring or the right ring. If the patient doesn't see a ring is spinning, then both rings are made larger until a spinning ring is detected. If a diop ring is detected as spinning, then both rings are incrementally made smaller, and the spin location and/or direction is randomly switched until a spinning ring cannot be detected. Diop subacuity is where the spinning ring is too small for spinning to be detected. Increasing the diop diameter from subacuity to the next largest diameter where spinning can be detected verifies that diameter as the acuity endpoint. False positives are easily detected by asking the patient, is the diop ring spinning clockwise or counterclockwise? The result is that a diop provides a rapid, precise, and consistent measurement of acuity regardless of patient literacy, culture, or age. Diop research has consistently shown that Snellen testing adds excess minus power and may be a contributing factor in the global epidemic of myopia. The increased precision, accuracy, and efficiency of a diop is likely due to the diop stimulus gap being half the area of the Snellen stimulus gap. As a result, diop testing is up to 6 times more accurate than standard Snellen testing. Diop testing is up to 8 times more precise than standard Snellen testing. Diop testing is typically twice as efficient as Snellen testing. Diop acuity tests typically take only 10 to 20 seconds per eye. Diop refractions typically take only 90 to 180 seconds per eye. But why do we see in color? When light passes through the cornea and lens, each color of light has a different focal depth in relation to the retina, even though the rear color responsive photoreceptors are the same distance from the lens. Red is focused behind the retina, green is focused on the retina, blue is focused in front of the retina. Visual acuity is regulated by the focal depth of those colors of light as perceived by the red, green, and blue responsive photoreceptors in the fovea at the back of the retina. However, not everyone sees color in the same way. Individuals with a stable near image have a 50% red and 45% green ratio of photoreceptors. Individuals with near vision stress have a 75% red and 20% green ratio of photoreceptors. For instance, dyslexia is a literacy problem, which seems to have little to do with reduced intelligence. Instead, however, dyslexia seems to be associated with near vision stress, which reduces the ability to read letter-based words. A simple and rapid test for near vision stress is possible by using a blue on black diop versus a green on white diop to indicate whether or not a person has that near vision stress. As identical diameter diops get smaller or you move away from the screen, which diop are you better able to see spinning, the blue or the green? Being able to see a smaller spinning green on white diop rather than the spinning blue on black diop indicates a stable near image. Being able to see a smaller spinning blue on black diop rather than the spinning green on white diop indicates near vision stress. Having near vision stress indicates that a person has potential symptoms of dyslexia and possibly symptoms of migraines and epilepsy. How well does it work? The diop color screening test using a blue on black versus a green on white spinning diop has a 90% correlation for diagnosed symptoms of dyslexia. Diop vision testing is also possible with infants as young as 14 weeks of age. Diop testing for large groups may be done easily and rapidly by comparing the diop diameter where spinning is first detected versus the diop viewing distance. Diop testing for low vision is inherently more precise than Snellen testing. Our goal is for the diop test to become the 21st century standard for global vision testing. Welcome to the diop revolution, helping the world see clearly, one person at a time.